Good morning, everyone. My name is Arjun Viral. Today, I'm really excited to presenting the topic that I think incredibly relevant to every one of us who uses the internet. The topic is impact of storage latency on cloud application performance. Now, before I begin, let me ask you a simple question: how many of you ever opened a website or app which take very long to load, took forever to load? Almost everyone we have faced this issue. Now, here's the interesting part. Most of the time, we will blame the internet or the service provider or the developer who wrote the back who wrote the code for the application. But actually, in most cases, the real problem is hiding much deeper inside the system. It is something called the storage latency. By the end of this presentation, you will understand exactly what storage latency is and why it matters so much and how it affects our real business in our world. Most importantly, how our engineers will fix it. So let's get started. Let's begin with a basic question. What is storage latency? For- Uh, if we take a very simple example first, we will do in everyday. Imagine you are sitting in a restaurant. You order your food. Now the time taken between the when you place your order and the waiter actually brings your food to the table, the waiting time, which is known as the latency. In the world full of computers and cloud systems, it works exactly the same way. When your application needs some data, maybe your profile picture, your shopping cart, your bank balance, it sends a request to the storage system. The time it takes for the data to come back is called the storage latency. In cloud environment, this is measured in very small units, such as microseconds to millisecond. 1 millisecond is 1,000 of a second. Sounds very small, right? But here's the thing. Modern apps don't just make only one request. A single page load on a website might involve 50, 100, or even 200 individual data requests. So if each request take even 10 extra milliseconds because of the storage latency, are suddenly looking at a 1 to 2 extra second just from the delays alone. So if we look at the definition, so here's the definition. Storage latency is the time delay between a request for data and the moment that the data is delivered. In cloud environment, it is measured in microseconds to milliseconds, as I already said. So look at this block diagram. This is the total latency window. This is the flow of the latency. First, first app request, which goes to the network and storage IO, then go to the data transfer and the app response. So I will explain this. Your app sends a request. It goes over the network. It triggers a storage read and write operation. That is, which is take place inside the storage. Then the data gets transferred, and finally your app responds to the user. The entire chain is the total latency. Now here's the one important distinction I want to make here is the latency is not same as bandwidth because bandwidth is like a width of a road. A wider road can carry more car at once. That's more bandwidth, more data per second, we can say. But latency is like the distance to your final destination. Even if the road is super wider, if you're driving very far, it still takes time. So we can simply say that we can have a super fast, high bandwidth internet connection and still have a terrible latency. That's why we need to understand and optimize latency separately. The storage latency is often described as the single biggest bottleneck in cloud application performance. That's what we will be exploring today. If we see, they have mentioned them as a single bottleneck effect in cloud app performance. And also it differs from the bandwidth. Latency is delay, bandwidth is data volume per second. So next we are going to see that the types of cloud storage and their latency. So the types of cloud storage and their latency. If you look at them, uh, the first the first we have is the in memory. Uh, but here's something really get interested. Going on and just get interesting. Not all storage is the same. There are different types of cloud storage, and they have very different speeds. So let me walk through you each one. Think of this like a different type of transport system. Some are very super fast, and some are very slow, but each one is useful for different application or purpose. First, in-memory storage. The in-memory storage is the session data, real-time fetching. The latency, if you look at, is less than 1 millisecond. Tools like Redis and Memcached, this is the fastest storage that exists. The latency is under only 1 millisecond. How is this possible? You you may have the question. Because the data is stored in random access memory. The computer's working memory, not in any other physical hardware such as disk. You know, accessing RAM is almost instantaneous. We can access anywhere, anytime if we want to. This is used for things like session data, real-time paging, shopping cart contents. Think of this like having the answer already in your head. No need to look anything up. That's why the latency is very small, less than 1 millisecond. Second, second is the NVMe SSD, local instance. NVMe stands for the non-volatile memory express. These are extremely fast solid state drives. The latency is zero point 0.1 to 1 millisecond, used for active databases and hot data. We can say, in other words, we can say this like having your notes right in front of your desk, so you can easily read it. That is called the local instance. Third is the cloud block storage, like AWS EBS or Azure Disk. Latency is 1 to 10 millisecond only. This is your standard storage, used for operating system volumes and application data. Think of this like a well-organized filing cabinet in the same room as you. So this is the third one, which is used for voice volumes and app data. The fourth one is the network attached storage. Latency jumps to 5 to 30 milliseconds, and this is a shared storage. Multiple servers can access it over a network. Think of this like a filing cabinet in another room. Filing cabinet in another room. You have to walk over and get the file. So this is the network attached storage. So the fifth one is the object storage, like Amazon S3, Google Cloud Storage, or Azure Blob. The latency is about 50 to 200 milliseconds. Uh, this is used for media files, backups, logs, and static website contents. Think of this like going to a storage warehouse outside a building. It takes time to go there and come back. Sixth one is the cold and archive storage. Latency here is not in milliseconds. It is minutes to hours. This is for data you almost never need to access. Long-term complaints records, old backup, disaster recovery archives. Think of this like a data stored in a warehouse in another city. You don't access it often, but it's very cheap to store. So this is the key lesson is here is your choice of storage type has a massive impact on your application speed, and engineers have to carefully decide which data goes where, based on how frequently it is accessed and how fast it need to be served. So this is the types of cloud storage and their latency. Now we are quickly gonna look into the how latency affects the application types. So now let's look at how latency travels through a typical cloud application. Most applications are built in what we'll call a three-tier structure. So let me show you. So the three-tier structure is this: presentation tier, application tier, the data tier. So the ground floor is the data tier. This is your like a database storage system, your file servers. This is where all the data lives. Uh, The middle floor is the application layer, your backend server, your APIs, your business logic. This is the brain of our application. And the top floor is the presentation layer, the website or mobile app that the user actually sees and interacts with. Now, here's what happens when there's a storage latency at the ground floor. A slow database query at the data tier causes the application tier to wait. The API call takes longer. The business logic is delayed. All of this then reaches the presentation time, and the user sees a spinning loader, a timeout error, or a blank page. We often see it, and that's not a one-to-one relationship. A 50 millisecond delay in the database doesn't cause a 50 millisecond delay for the user because every layer adds its own overhead. By the time the delay reaches the user, it could be easily about 300 milliseconds or more. Modern application makes this even more complicated. Today, app uses something called a microservice architecture. Instead of one big application, you have dozens of small services that talk to each other. Each of those services might make it one storage service. So a single user action might trigger 10, 20, or even 30 storage requests, each one with its own latency. All of that adds up. This is why storage latency is so dangerous. It is invisible to the user, but it affects, but its effects are felt everywhere. So next we are going to see these two. Real world performance impact. Okay, now I want to show you something that I think will really make this topic hit home. Real world data on how latency affects business. These are not just made up numbers. These are findings from some of the biggest companies in the world. So let's take a look. So this is the storage type is a response time impact on our real world businesses. So Amazon conducted an internal study and found that just 1 millisecond of extra latency caused a 7% drop in conversion. 7%. Think about what that means for a company that processes billions of dollars in transactions. 1 millisecond. That's almost nothing in human terms, but it's devastating in business terms. Google found out that for every 100 milliseconds of added delay, that's one tenth of a second, they experienced a 1% loss in their revenue. If uh, if 1% revenue loss again for a company at Google scale, 1% is an enormous amount of money. And here is another one. A research shows that if a page that takes more than 3 seconds to load, 53% of mobile users abandon it. See, more than half of the users will abandon it. They will just leave. They don't want to wait. They don't want to waste their time. And finally, a 1 second slogan reduces customer satisfaction scores by up to 16%. So even for 1 second and 3 seconds, the users will just leave like 50% of the users. Now look at the chart on this slide. It shows the response time for each storage type. See how the cold archive storage shows 18,000 milliseconds. That's 18 seconds. Compare that to memory storage at 1 millisecond. The difference is 18,000 times. If someone built an app that accidentally fetched a live user data from the our archive storage, the user should have to wait 18 seconds for every action that is going to take in that app. The app would completely become unusable due to the so much delay. This is why I say storage performance is not just a technical metric, it's a business metric. It directly affects our revenue, user attention, and brand reputation. Look at NVMe SSD, in-memory, block storage, and emails. They have very small latency. We just saw in the previous one. But the cold archive has 18,000, which is 18 seconds for every action. So that's why it will become completely unusable by the user. So now next we're gonna dive into the topic called the latency versus throughput versus IOPS. Before we further go further, I want to clear up three terms that confuse a lot of people: latency, throughput, and the IOPS. You'll hear this constantly in cloud and storage discussion. We already know what is latency. We have been covered it. It's the time taken for the single operation to complete. But under how long does it takes for a request to be answered? This is what users feel directly. Lower is always better. So this is latency. We already saw it. Now we look into the throughput. Throughput is the amount of data transferred per second. This is the total amount of data that can be transferred per second. It is measured in megabytes or gigabytes. This matters when you are moving a large amount of data, like video streaming. Now I am recording the data analytics, bulk file transfer. High throughput means you can move more data in less time. So throughput should be more for our users. And IOPS, which is the input output operations per second. This is the number of read write operation your storage can handle every second. This is critical when you have many users accessing your system at the same time, like a busy e-commerce website during a Black Friday or sale, or bank or during business hours. We can say like that. Here's how to think about them together. Imagine a highway. Latency is the we can name them as a it's a speed limit. How fast can one car go? Throughput is the number of lanes. How many cars can travel at once? IOPS is the how many cars can enter and exit the highway per second. So, can you imagine this? You need all three to work well. Fixing one while ignoring the others won't solve the issue here. So we need to work all the three well. Then only our website or app will be very fast for the users. Now next we are going to see about the database query performance. So where the time goes in a database query. Now we are going to look into this. Let's go deeper into this most common sources of the storage latency. Uh, when your app asks the database a question like show me all the orders for the user, where does the time go? Look at the breakdown on the slide. Only 10% of the time spent on the CPU processing, the actual thinking. 15% goes to the network round trip, and 50% goes to the data transfer, and 55% goes to the more than half is going to the spent time spent waiting for the disk and the storage area, just waiting for the storage to fetch the data. More than half of the time has been gone to the storage. This is why when a database is slow, the fix is almost always storage related, not code related. Some practical examples of this: if you are still using old spinning hard drives instead of SSDs, your full table scans can be 100 times slower. Every missing database index means the system has to scan every single row to find the answer. More discrete, more latency. Connection pooling, where you reuse the existing database connection instead of opening a new one every time, and it reduces overhead significantly. Uh, catching query results in Redis means common queries don't even touch the database at all. These are not complex changes, but their impact is very enormous. So this is known as the database query performance, which is the common source for our storage latency. Now we will look into the user experience and the latency tolerance. Now let's talk about the human side of this. How do users actually experience the latency? So if you see the slide, research in user experience tell us what human perceive response time in a very specific way. Under 100 milliseconds feels completely instant. The user doesn't notice the delay at all. This is a gold standard that every app should aim for. 100 to 300 milliseconds, there is a very slight delay, but the users find this acceptable, good experience only. So this is also acceptable value. 300 milliseconds to 1 second. Users start noticing the delay. There's a tiny bit of frustration. They might wonder if something is wrong. 1 to 3 milliseconds. This is a poor experience. Users disengage. They might open another tab. They lose confidence in the particular app. So they just abandon. Over 3 seconds, unacceptable. We already saw that 53% of mobile users have already left by this point. Over 3 seconds is very enormous and long. There is something very important. First impressions are permanent. Research show that 79% of users are less likely to come back to a website after a bad performance experience. Not just they will just be annoyed, they literally won't return. The question isn't how much latency can we afford. The question is how close to 100 millisecond can we get, which is instant and feels immediate. So this is the user experience and the latency tolerance. So now let's get into the measuring and the benchmarking of the latency. See, all right. Now we understand the problem. How do we actually measure it? Because you cannot fix something you haven't, measured. There are several great tools for this. The first tool is the FIU, Flexible I/O Tester. This is the industry standard tool for storage benchmarking, marking. It stimulates different kind of read and write patterns. It tells you exactly what is your IOPS, latency, and throughput numbers patterns are. Next is the DD, a basic Unix command to test sequential read and write speed. Very quick and easy to run on a Linux system. Next is the IO ping. IO ping that measures real-time block device latency. Great for a quick health check of the your disk. For cloud environment, AWS CloudWatch gives you built-in matrices for EBS, volume, and RDS databases. Things like volume read latency and the volume write offs. These are the tools which are used for our cloud environments. Prometheus and the Grafana. The Prometheus. Prometheus and Grafana together will give you a powerful open source marketing stack. Prometheus collects the matrices every few seconds, and Grafana turns them into the beautiful dashboard with alerts. And for database specific benchmarking, pgbench for PostgreSQL and sysbench for MySQL. Simulate a real query workload with multiple concurrent users. The most important best practice we can share here is the always measure P50, P95, and P99 latency, not just the average. The average can look completely healthy while your slowest users are having a terrible experiences. P99 tells you what is the worst 1% of user experience. This is where your real problems get hidden. So these are the measuring marking under the latency. Now we will dive into the one of the most powerful and the cost-effective way to reduce the storage latency, which is the caching. Caching simply means storing a copy of data somewhere fast, so you don't have to go all the way back to slow storage every time. There are the several layers of caching, well-designed system. Client slide cache. Client slide cache. This is the cache in your browser or mobile app. When you visit a website for a second time and it loads faster, that's a client side caching. Response time is nearly 0 milliseconds. CDN cache. The CDN cache is the second block, the content delivery network. Store copies of your static content on server around the world. When a user requests a content, it comes nearest CDN server, not on your origin place, but under 5 milliseconds it comes to the near server typically. So the next one is the application cache using Redis or Memcache. This is where your backend caches database query results, API response, and session data in memory. Under 1 millisecond, if 90% of your query are answered by the Redis, your actual database barely has to work. So this is the application case using Redis or case. Next is the database query case. It's a database engine itself catches the result of frequent queries. The same query runs again. It returns the catched result immediately without touching the disk. So this is the database query case. A well-designed multi-layer caching strategy that can reduce effective storage latency from 150 milliseconds all the way down to under 1 millisecond for the majority of the requests. That is 150x, 150 multiple times improved. So this is the best for the caching strategy. This is one of the best caching strategy to reduce our latency in the cloud. So this is the caching strategies for the reducing the latency, storage latency. Now let's we get into the CDN and the edge computing solutions. Let me expand on CDN and edge computing because this deserve a bit more attention. Imagine your cloud server is located in the United States. A user in Chennai sends a request. The request has to travel from all the way Chennai to the US and all the way back. So the distance alone adds up to 150 to 200 milliseconds of latency. You cannot compress the law of physics. Okay. So this is where the CDN and the edge computing solves the problem. The CDN has edge servers that is placed in cities all over all over the world, in India, Europe, US, Southeast Asia, everywhere in the world. When a user in Chennai makes a request, it goes to the nearest edge server, maybe even one inside the India. The response time drops dramatically. This achieves up to 50 to 80 percentage reduction in the latency for geographically distant users. That's very huge for the peoples. Beyond speed, the Edge network also provides DDoS protection. Attacks traffic get absorbed at the edge before it ever reaches your origin server and your storage system. They provide auto scaling, traffic spikes, and they get distributed across edge node instead of hammering your main server. And they provide better availability. Even if your origin server has a brief issue, cached content can still be served from edge nodes. For any app with users in multiple cities or countries, CDN is not an option. It is an essential infrastructure for the people. So this is the main advantages of the CDN and the edge computing solution. Now, let me give a practical framework for making storage decisions. So choosing the right storage type is the most important thing for the cloud applications. So this is the storage type best and their latency and their cost and their services. So first, the simple rule is the more frequently the data is accessed, the faster the storage should live in memory case. For your hottest, most frequently accessed data sessions and real-time feeds, shopping carts, super fast, but it is very expensive. Use it selectively. So there's a $4. $4 symbol has been mentioned, which is very super expensive. Example services are Redis, Memcache, Elastic. These are the examples. And local NVMe SSD, which is best for the databases active workloads. And their latency is about zero point 0.1 to 1 millisecond. And this is also super expensive, but it is fast and reliable. The example services are the EC2 and the instant storage. Next one is the block storage. This is which is our SSD. Best for OS volume apps and DBs. Examples are like AWS EBS GP3 and Azure Premium, which is best for our operating system application files. Good balance of speed and the cost, we can say this, and file storage units. This is for the shared file systems and CMS. The latency is more 5 to 30 millisecond, but this is very cheaper from the previous ones, from the previous storage. AWS, EFS, and Azure files are the example services. And the object storage. These are the media logs, static assets, which is best for the static assets, media and logs. The latency is about 50 to 200 milliseconds. This is also very cheaper. Example services are Azure Blob, GCS, Google Cloud Storage, and S3. The last one is the cold active. We already seen that how much delay latency this cold storage get caught. 18 plus minutes it will cut. So it is very, very cheaper, and many of them will consider them as, you know, wasteful. This is cost efficient, but the speed is very, very poor. So for the data which is almost never touched, in old complaints like that, you pay almost nothing, but the retrieval will take hours. The glacier is the examples are the glacier and the orchestra. The biggest mistake teams make in putting everything onto the one storage type, active database in the object store, which is terrible. Old locks in NVMe SSD, which is very wasteful. Match the storage to the access pattern, so it will be very fast and cost efficient. So the next thing is the case study, e-commerce application. Let me show how a real world case study that brings everything we have discussed together. Before optimization, all the data served from HDD based block storage, no caching, every request hit the database, single region deployment. Users are very far away. Average load time is 4 seconds. Cart abandonment rate is 68%, and the monthly infrastructure cost is $12,000. Now, after the optimization, how it changes. Product catalog caged in Redis are less than 1 millisecond reads. NVMe SSD block storage for active DB volume. CDN deployed across 3 global regions. Average page load time is 0.8 seconds. So, which is 81% in the decrement from the before optimization. Cart abandonment rate is 42%, minus 38% improvement. Monthly infrastructure cost is $9,500. So which is minus 21%. The results are 81% faster the page loads, 38% fewer abandonment cost just by fixing our storage latency. Now next is the monitoring tools and the alert strategies. AWS CloudWatch, which is the cloud native. It monitors EBS, volume, read latency, and write latency. Sets alarm at P99, which is greater than 10 millisecond for SSD volume, and uses dashboard to correlate storage and for the app matrices. Datadog APM, which is a full stack, so auto trace DB queries and storage calls. Flame graph shows exact latency per layer. Anomaly detection for sudden spike, we can go for the Datadog APM. Prometheus plus Grafana, which is the open source. Node exporters grabs disk I/O for every 15 seconds. Grafana panels for IOPS latency and queue depth. Alert managers to send Slack or pager duty alerts. And new relic, distributed tracing across microservices. Storage layer timing in every transaction. Baseline and alert on latency deviation, which is a software as a service. Now, next is the best practices under optimization tips. Storage selection, caching, database tuning, architecture, network, and monitoring. These are the best practices and optimization tips for the latency. First is the storage selection. It matches the storage type to the data access frequency. We can use like NVMe SSD for transactional database. Caching. We can implement Redis for session and query cache and database tuning. Index all column used in where and join classes. Use connection points such as PG bouncer, proxy SQL. Then is the architecture. Place and compute storage in the same region. Okay. Then the network. Use VPC endpoint to reduce internet latency. Enable jumbo frames for large data transfer. Monitoring. Alert on P99 latency, not just P50 averages. We already seen that P99 latency is only one the it alerts all the it monitors. Track storage queue depth as an early one. So the summary and key takeaway from this session is the storage latency is the number one bottleneck effect in the most cloud application. So choose the right type from day one. In memory caching, reduce effective storage latency from 100 milliseconds to under 1 millisecond for hard data. Always benchmark with P95, P99%. Average latency hides the worst user experience. CDN plus edge computing reduces geographic latency by 50 to 80% for global distributed users. Every 100 milliseconds of extra latency costs 1% in revenue. Storage performance is a business metric, main business metric. Database indexing, connection pooling, and read replicas are high impact and low cost optimization. Monitor continuously. Set triple P99 latency SLOs, alert and queue depth, track cache hit rates daily. Okay. These are the summaries and key takeaways. Now the last thing I want to say is the performance is a future. Storage latency is the foundation of cloud app performance. So these are the summary and key takeaways from the storage latency impact on cloud application performance. So thank you.